The essence of this narrative is the examination of measurement errors in statistics. Measurement errors refer to the disparity between a measured quantity and its true worth. These variations aren't simply mistakes. They're inherent constituents of the measurement process. Two types of errors constitute measurement errors: random errors and systematic errors. Random errors lead to inconsistent values during repeated measurement of the same quantity. On the other hand, systematic errors aren't owing to chance. They're caused by intrinsic, repeatable processes of the system. Measurement errors can be understood through their impact on accuracy and precision. In statistical discussions, when these errors are boiled down to randomness or a probability theory, related uncertainty, they're referred to as errors. Every repeated measurement with a sensitive tool offers slightly different outcomes. The statistical error model suggests that the error usually has two additive parts: the constant systematic error and the varying random error. Systematic errors are sometimes called statistical bias. They can often be reduced through standardized processes. Part of the educational journey in the sciences involves learning to use standard instruments and protocols to minimize systematic errors. Random errors are due to uncontrollable factors. While it might seem sensible to control these random errors, doing so could be too expensive and impractical. This could be due to the changing nature of what we're measuring, or the inherently probabilistic nature of the measurement, as seen in quantum mechanics. These errors particularly rise when instruments are pushed to their operational limits. The two components of measurement errors are random and systematic errors. The former is omnipresent, arising from unpredictable fluctuations in measurements or the experimenter's interpretation of the readings. They can be estimated and reduced by making and comparing multiple repeated measurements. Systematic errors are generally constant or proportional to the true value. They typically result from inadequate calibration of instruments, imperfect observation methods, or environmental interference. They can generally be identified, and if so, usually eliminated. Incorrect zeroing of an instrument exemplifies systematic error in instrumentation. In the realm of experimentation and measurements, random and systematic errors play a significant role. Random errors primarily arise from unpredictable fluctuations in measurement readings, which can be influenced by environmental interferences or subjective interpretation issues. This concept of random error is tightly bound to precision. Higher precision tools have lower variability or standard deviation and fluctuations. Systematic errors, on the other hand, can occur due to calibration discrepancies, zero errors, environmental changes, or imperfect observation methods. For instance, consider an experimenter recording the time of a pendulum swing. If the timer is inaccurately set to start from 1 second, all results will be shifted by this zero-error. Repeated experiments amplify this discrepancy, leading to a potentially significant percentage error in the final average result. Furthermore, distance measurements via radar will be consistently overestimated if the slowing down of waves in air is not factored in. This showcases systematic error in instrumentation. Similar errors can crop in mathematical or physical models too. For instance, if the slight movement of the pendulum support during its oscillation is overlooked, this will result in systemic errors. Systematic errors can be constant, directly proportional to the actual value, or correlated with a separate quantity whose reading may be impacted by environmental factors. For example, a thermometer influenced by a systematic error of 2 of the actual temperature will record varying degrees of inaccuracy based on whether the actual temperature is above or below 0. However, systematic errors that fluctuate over the course of an experiment, drift, can be more easily detected. They provide a temporal trend more so than random variations around a mean. If consistent drift is observed in a measurement of a fixed quantity over different iterations, or if the instrument used exhibits signs of warming, which may impact the reading, it signifies a possible drift. This can be controlled by regularly checking and adjusting the zero reading, ensuring accuracy throughout the study. In essence, if zero readings are persistently off, a systematic error has likely crept in. Understanding systematic errors in measurement is vital. In order to identify these errors, one must methodically analyze a series of collected data. In cases where a pattern may not be immediately evident, it is necessary to compare observations against known standards or using tools of higher precision. For instance, if a stopwatch's accuracy is in question, you can compare its readings with the precise timing of a telephone-speaking clock. If the stopwatch is discovered to be running fast or slow, the recorded data needs corresponding adjustment. Periodically, instruments such as voltmeters and ammeters must be verified against recognized benchmarks. Systematic errors can also be detected by utilizing these tools to measure quantities that have already been established. A case in point is when a spectrometer equipped with a diffraction grating is calibrated by using it to measure the exact wavelength of the sodium electromagnetic spectrum lines. If a systematic error is constant, it presents a unique challenge as its impact is detectable only if removed. This kind of error cannot be eliminated by merely redoing or averaging many results. Calibration of the measurement instrument is a typical method of correction. Random or stochastic errors, which are unpredictable, occur in a measurement randomly from one reading to the next. They're customarily distributed in a normal pattern due to the central limit theorem, particularly when the stochastic error results from several independent errors. Observational error is a term often employed to describe errors like response errors and other non-sampling errors. In situations like surveys, inaccurate data collection, wrongful recording of responses, and recording inaccurate responses can contribute to errors. These errors can either be random or systematic. Specific tools are devised to assist researchers in formulating precise survey questions to minimize errors. It's important to note, however, that regression coefficients and hypothesis tests become unreliable if one or more independent variables are measured inaccurately, causing attenuation bias.